In this section, we define the concept of free energy and explain how free energy is related to the spontaneity of a chemical or physical process. So if we consider an exothermic process, that is one that has delta H being less than 0, but that also has delta S being greater than 0, what do we know about the system? Well, we know that the surroundings will be heated because our chemical reaction or our physical process is releasing heat into the surroundings. As we're heating up the surroundings, it's not surprising that the entropy of the surroundings will increase. So what we know at this point is that delta S of our system and delta S of our surroundings, because they are both positive numbers, when we add them together, their sum will be greater than 0. And as a result, we know that any process that has delta H negative and delta S greater than 0 will always be spontaneous. So what about the other combinations of delta H and delta S? What about if we have an endothermic process, one with delta H being greater than 0, that has delta S being less than 0? Well, we're taking heat from the surroundings, we're cooling them down, so therefore delta S of our surroundings will be less than 0. So delta S of our system is negative and delta S of our surroundings is also negative, so when we add those two numbers together, we'll get a negative number. So delta S of the universe will never be positive for this kind of system. So if delta H is greater than 0 and delta S is less than 0, what we know is that system will never be spontaneous regardless of the conditions. Okay, so we've got two more possibilities to look at. What about if we have a system that is endothermic, that is delta H is positive, and it has a delta S system also being positive? Now, because we're taking heat from the surroundings will be cooled down, and as a result, the delta S of the surroundings will be negative. So in this case, to calculate the delta S of the universe, would be taking a positive number and adding to it a negative number. So this process could be spontaneous or it could be non-spontaneous, depending on the relative size of the entropy changes of the system and the surrounding. So it's kind of, sort of a little less decisive in this case, right? It's a bit more ambiguous as to what the scenario might be with respect to spontaneity. What about if we have an exothermic process, that is one that has delta H negative, that has a delta S of the system being negative? So we're releasing heat into the surroundings, so that will increase the entropy of the surroundings, so delta S surroundings will be a positive number. So when it comes time to calculating delta S universe, we know that we have a negative entropy change for our system and a positive entropy change from our surroundings. So depending on the relative size of these two guys, we could have delta S universe that is either positive or negative. That is, our process could be spontaneous or non-spontaneous. It just depends on the size of these two quantities. So the question becomes, can we narrow down the conditions for those two ambiguous cases that kind of allow us to say a little bit more about when these types of processes will or won't be spontaneous? So we know that for an isothermal process, that's one where the temperature is not changing, that the entropy change of the surroundings is just equal to the heat transferred to or from the surroundings divided by the temperature of the surroundings. And we defined enthalpy as being the heat that is transferred at constant pressure. So we can substitute the heat transferred from the surroundings or to the from the system or to the system by the enthalpy change of the system. So what we're really saying is that we can define the entropy change of the surroundings as being the negative of the enthalpy change of our system divided by the temperature of our surroundings. So if we put that back into our expression for the entropy change of the universe, we end up with this. The entropy change of the universe is equal to delta S of the system minus delta H on T, this is minus delta H on T. The T refers to the temperature of the surroundings. Now what's really cool about this is that we can make measurements on our system and find out what's happening in the whole universe, and we can get both of these quantities from the tables that are in the back of our book. So that's really cool, right? We can figure out what's happening in the broader universe, and we can determine the spontaneity of a process or the non-spontaneity of a process just by using those tables that are in the back of the book. So this is kind of cool. What we're going to do now, though, is a little bit of sort of like a mathematical convenience. Is we're going to take our expression for delta S of the universe and we're going to multiply everything through by minus T. So what we end up with is this expression here, minus T delta S universe equals delta H minus T delta S. The quantity that first term there is referred to as the Gibbs free energy, and it's given the symbol delta G. It's called the Gibbs free energy in honor of this guy who is called Josiah Willard Gibbs. He was the first person in the USA to obtain a PhD in engineering and who defined the mathematics that describe this. So why do we define delta G? What makes it useful and what does it represent, and why the heck is it called free energy? Well, the first thing to recognize is that when we express T in Kelvin, it's always greater than 0. So when we take a positive number and we multiply it by a positive number, then these things and then we take the minus of that, we would get a negative number. So what this means is that for a non-spontaneous process, delta G is always greater than 0. If a process is spontaneous, delta G will be less than 0. If delta G equals 0, then nothing's happening. We're just under a set of conditions that we'll later learn about as being called being at chemical equilibrium. What does delta G represent? Delta G represents the energy that is available for useful work, and I'm going to illustrate what I mean by that a little bit more in the next slide. So here we have delta G equals delta H minus T delta S. So delta H is the energy that is transferred as a result of bond breaking and bond making. It's like the total energy that is released or absorbed in your chemical or physical process. As we mentioned, delta G indicates the energy that's available for useful work. So what's this guy? Well, that's the energy that becomes dispersed during the transfer process. So why do we lose some of the energy? Why don't we have all of the energy from bond breaking and bond making being available for useful work? Well, the reason is because in any energy transfer process, some energy is always spent increasing the entropy of the universe, right? Because in a spontaneous process, the entropy of the universe always increases. So basically, when you move energy from one place to another, you have to pay the tax man. You have to spend a little bit of energy increasing the entropy of the universe, and that energy isn't available for useful work. Okay, so we're now going to define this thing called the standard Gibbs free energy of formation. So it's a standard Gibbs free energy, but then we add the little f there to indicate that it is talking about the formation of a compound. And the standard Gibbs free energy of formation is defined as the free energy change accompanying the formation of 1 mole of a substance from its elements under standard conditions. So it's very, very similar to the standard enthalpy of formation that we talked about previously. Something weird that can happen with this, because we're talking about the Gibbs free energy exchange accompanying the formation of 1 mole of a product, is sometimes we end up with fractional coefficients in our reactants. Don't worry about these reactions being written in a non-standard way. It's okay. So you will find large tables of Gibbs free energy of formations in the appendix of your textbook, alongside those standard molar entropies and the enthalpies of formations that we had been using previously. In Gibbs free energy, just like enthalpy, is a state function, so therefore we can do Hess's law type calculations similar to what we did when we were calculating enthalpies of reactions. And we can calculate the Gibbs free energy of a reaction using our tabulated Gibbs free energies of formations. We're just going to take the sum of the Gibbs free energy of formation of our products and subtract from that the sum of the Gibbs free energy of formation of our reactants. So very, very similar to what we were doing for enthalpies. So if I want to calculate the Gibbs free energy change for this combustion of methane here, then I would have to look up the standard Gibbs free energy of formation of each of my reactants and products, and then to get the Gibbs free energy change for the reaction, I'm going to take the sum of the product Gibbs free energy of formations, remembering that I have to account for each mole of substance, and then I'm going to subtract from that the sum of the Gibbs free energies of formations for each reactant, and then there I am, I get that number there, and in this case delta G is less than 0, so I know that this process is spontaneous. So Gibbs free energy for a reaction is a single quantity that allows you to decide if a process is spontaneous or non-spontaneous. This is kind of cool. We don't have to consider both the enthalpy, the temperature, and the entropy change in order to do this. So that's really cool. We've reduced the number of parameters that we need to look at down from 3 to 1. Okay, so when we consider this, we can use the Gibbs free energy to predict under what conditions a process will be spontaneous. So I like to make up a little chart like this, where I've got delta H on the x-axis, delta S on the y-axis, and then I consider each of the 4 quadrants and the conditions that would be required for a reaction to be spontaneous that fell in one of those quadrants. So let's begin with let's begin looking at the case where both delta S and delta H are positive. Okay, so delta H is positive, delta S is positive. Remember, the temperature is always positive. So delta H minus T delta S gives me the Gibbs free energy, and the reaction will be spontaneous when that quantity is less than 0. So then I'm going to add T delta S to both sides. So this is saying that when delta H is less than T delta S, then this process will be spontaneous. Now I'm going to divide both sides by delta S, and you'll see what happens. Now remember, with an inequality, if you divide by a quantity that is greater than 0, you don't flip the sign of the inequality. So don't flip. But if what you're multiplying or dividing by is less than 0, you have to flip the direction of your inequality. Remember that from your sort of elementary algebra class. In this case, no need to flip because delta S is greater than 0. So just divide both sides by delta S. So what I've concluded is that this process will be spontaneous when delta H, when the temperature is greater than delta H on delta S. That is, when both the enthalpy and entropy are positive, the process is spontaneous above a threshold temperature, and that threshold temperature can be calculated by taking delta H on delta S. I do just want to point out that delta H is commonly given in kilojoules per mole. and delta S's are often given in joules per mole per degree Kelvin. So you're going to want to times that guy by 10 to the 3 when you're doing these calculations of the threshold temperature. Okay, so we got one of our quadrants figured out. Let's move on to the next one. Okay, so delta H greater than 0, but delta S is negative. So I've got my delta G equals delta H minus T delta S. So delta H is a positive number, delta S is negative, and T is always positive. So this will be a positive number subtracting a negative number. So delta G will always be positive for these conditions. So when delta S is negative and delta H is positive, my process is always spontaneous. Okay, let's keep moving on and look at the next quadrant. What about if delta H is less than 0 and delta S is greater than 0? So in this case, we've got delta H being a negative number, and then T is always a positive number, and delta S is positive. So we're going to have a negative number subtracting a positive number. And so that would always be negative. Always be negative. So delta G will always be negative for this case. So that means that when delta S is positive and delta H is negative, your reaction will always be spontaneous. Okay, we've only got one case left, and that's when both delta S and delta H are negative. So when both of these quantities are negative, what do we know about the sign of delta G? Well, delta H is negative, and then we're going to subtract from that a negative number. So a negative minus a negative. So there, it depends whether this is positive or negative depends on how big this term is. So what we know is that this will be spontaneous when delta H minus T delta S is less than 0, when the Gibbs free energy is less than 0. So again, I'm going to just add T delta S to both sides, so that gets me to here. And then I'm going to divide both sides by delta S. Now I have to remember in this case that delta S is less than 0, so I need to flip my inequality when I do the division. So I divide both sides by delta S, and I flipped my inequality there. So this process will be spontaneous when T is less than delta H on delta S. That is, it's going to be spontaneous below some threshold temperature. Right? And that's when this is going to be spontaneous. Okay? And the threshold temperature is always calculated by delta H on delta S. Remember, like what I was saying previous, that often delta H's are given in kilojoules per mole, but delta S's are given in joules per mole, so you may need to multiply this guy by 1,000 if that's how your units are given. Okay, so now we have the complete diagram here, and this is worth having open in one of your tabs when you're doing a test or the final. And it describes the conditions under which a process will be spontaneous. So to judge spontaneity, you need to consider the enthalpy, the entropy, and the temperature of your system. Delta H, delta S, and T. When the entropy and the enthalpy change for your system are either both positive or both negative, there will be a threshold temperature that is important. When the entropy and the enthalpy change for your system have different signs, you will always definitively be able to say whether the process will be spontaneous or non-spontaneous without thinking about the temperature. So this is very, very useful information for judging whether a process will be spontaneous or not. So there are tables in the book, and you can find similar tables on the internet that summarize all of this information. I kind of like prefer the graph here. You know, it just kind of makes sense to me to have a picture of this rather than a table. But you can find other ways that these relationships are presented either in your book or on the internet. Okay, we did briefly mention this concept. We said that when delta G equals 0, no net change is occurring. So what does that mean? Well, what it means is that when delta G equals 0, the system is described as being at a state of chemical equilibrium. Chemical equilibrium. And under these conditions, the reaction is occurring in both directions, but the forward reaction and the reverse reaction are occurring at exactly the same rate. So there is no change in concentration of either the reactants or the products. It's just kind of like a stable sort of situation. The reaction isn't occurring in any net direction, neither forwards nor backwards. Now, I mentioned this because the overwhelming majority of your time in Chemistry 163 is going to be spent studying systems that are at chemical equilibrium. So let's kind of give an example of let's look at an example of a system that's at equilibrium. And a classic example of this is a stable mixture of a liquid and its solid at the melting point or at the freezing point. So we're going to take a mixture of ice and water, and we're neither adding nor removing heat. And then we're asking the question, at what temperature would the amounts of ice and water stay constant? So the system that we have is solid ice in the presence of liquid water, and we want the amounts of the solid and the liquid to just stay constant. We want to know the temperature at which that happens. So the first thing that I'm going to need is the enthalpy for this process, the enthalpy change for this process, and the entropy change for this process, and I can calculate those using tabulated values. So I've gone ahead and done that. Now what we're looking for is to know when is this system at equilibrium and there's not going to be any net change. What we're really asking for is when is delta G equal to 0. So we know that delta G is equal to delta H minus T delta S. Now, even though we're probably not going to be at 298 K, we're going to say that we can use the standard values that we got from the tables to be a good approximation of what the enthalpy and entropy are at this temperature of interest. So what we want is for this guy to be 0. That is, we want for delta H minus T delta S to equal 0. So then I'm just going to add T delta S on each side. What we want is for delta H to equal T delta S. Or alternatively, what we want is for the temperature to be equal to delta H on delta S. So when I do the math here, 6010 for my delta H for this reaction, 22 for my delta S, and that gives me a temperature of 273.18 K. So what I'm really saying is, if I have a mixture of ice and water, if I place that in surroundings that are at 0 degrees Celsius, there will be no increase in the amount of ice and no increase in the amount of water. It'll just be a stable system at equilibrium. There will be no net change. Okay, so if you could have an attempt at these 4 problems here before the Wednesday Zoom session when I'll be running through them, that would be very helpful.